This is lesson number 4 for Unit 6 for AP Calculus, and just kind of going back over what we've done so far in the first 3 lessons. We took the first 2 lessons to talk about methods for doing antiderivatives. Substitution is our key one, where you have a function of a blob and then the derivative of the blob hanging around. Just for fun, we also looked at integration by parts, another method to do antiderivatives. Those are the tools of the trade. And then last day, we started to look at how you might apply these tools to things more than just finding areas under curves. You might want to go and solve some differential equations. Last day, the nice thing about the differential equations, even if they were long and tedious, just going to go back half a page, even if they were long and tedious, the nice thing about the differential equations was that on the right-hand side, we only had independent variables. Just t in this story here. So you could easily integrate and then you were there. It might take a little while, but you were there. We didn't have the dependent variable on the right-hand side. That's all going to change now for lesson 4. We're going to look at our other situation for differential equations. This is the other key one that we are expected to solve for Calc AP, and that's what we call a separable differential equation. And in terms of instruction, wow, this is going to be brief. I got one line here. These DEs, these differential equations, can be solved by separating the x's and y's. That's it. That's the instruction. We need some on-the-job training. So we're going to try this out with 5 different examples. Each one has, a little curveball to it, right? So just when you kind of feel like you've got your feet under you, there's going to be another little issue thrown at you. But right off the start, I can tell that this story is different. And that's because this differential equation, it's written in terms of a derivative. Okay, that's fine. It's got the y prime, the dy dx. But there's this. That's actually the answer showing up on the right-hand side. That makes this much more challenging than last day. Okay, so we've actually got the dependent variable, the answer variable, showing up over here. So this is a big change. Simply trying to integrate it won't work because you don't know what y actually is. In fact, that's your goal, is to try to find y. So we're going to do this process of separation. We do this when we see both independent and dependent variables on that right-hand side. Technically, even last day we were doing separation of variables, but we just didn't have to talk about it that way. So I'm going to look at this differential equation this way. I'm going to separate this with a little bit of colors for the first 1 or 2. I'm going to say I've got dy dx, so I'm going to use green for the y's and blue for the x's. And that's equal to, over here on this side, 6x squared plus 1, all sitting on top of, looks like 3y squared. And again, the y is actually the answer. So my hope is I can separate this thing and have over on one side of my equation, I'm going to put all of the terms that have y's in them. Okay, so the y's are going to go this way, while the x's go in the other direction. Now, if you're going to ask, sorry, not x squared, but x's, if you're going to ask, wait, why did the 3 go as though part of the y's? How do we know it's part of the y's? It doesn't really matter, but as convenience here, I'm going to take it with me when I do the separation. So I need to get the green stuff on one side and the blue stuff on the other side of my differential equation. And when I do that, I'm going to end up with 3y squared multiplied by a dy is equal to 6x squared plus 1 multiplied by a dx. Once you've got it separated, and again, nobody really cares, where this 3 would go, but it sure is handy to put it on that side. Once you've got it separated, then you accomplish this task by integrating both sides. So I'm going to integrate the left-hand side with respect to y, and I'm going to integrate the right-hand side with respect to x. And when I do that, I end up over on that left side with a y cubed plus some sort of constant. I'll call that constant number 1. And then over here, I'm going to have, when I integrate using x's now, I'm going to have 2 x cubed plus an x plus some other constant, plus constant number 2. And I'm now going to go and try to solve for y, right? My goal is to go find y, right? It's my mission. So if I get that y by itself, I'm going to end up blending these constants together. So in the end, it turns out I don't really need to put constants on both sides. I'm also going to drop my green color here now at this point and just say, okay, y cubed, you're going to be 2 x cubed plus x, plus just one constant. I don't really need to have a couple of constants in there because I'm just trying to find something that's going to make this all perfect anyways. Last move in order to solve this one, to solve for y, I'm going to take a cube root. If you're bothered by those c's all turning into 1c, don't worry. As we do a few more, I think you'll see the flexibility here and understand how that works. But as I go to solve for y, I'm going to take a cube root. I'm now finding y, which is made up of x's. It's a cube root of this trinomial over here. So it's the cube root of 2 x cubed plus x plus c. Okay, I don't have to put down any plus or minuses. Odd roots never have any plus or minus issues. Now some of these stories will have plus or minus issues, so I'm actually pretty thankful that this one here does not. I'm going to leave a little note. Odd roots, like cube roots or fifth roots, don't have plus or minus problems. You'll wish that was true when we see the next example, but for now, so far so good. I do need to find that c though, so I'm going to go and take that initial condition. They told me about an x and a y value that go together. They have said when you put, it was right up at the beginning of the question, they said when you put 3 in for x, right, this is an x value going in here, when you put 3 in for x, you get 4 out for y. All right, I'm going to go and use that right now. I'm going to say, all right, y of 3 specifically is going to have to end up being 4. Well, that'll be the cube root of 2 times a 3 cubed plus a 3 plus the c. That's got to be 4. Tidying this up, I get the cube root of 57 plus c has to be 4. I'm going to cube both sides. When I do, I don't have to stare at the root anymore, and I have 57 plus c is equal to 64. So c is equal to 7. And I'm now ready to write my answer in. Here's my solution for my first separable differential equation. This y, which is made up of x's, is actually the cube root of this big mess. It's going to be the cube root of 2 x cubed plus an x plus a 7. And in this story, that 7, it's inside that root. It's not tacked on like after the root, it's actually inside it in order to get this to work. So that's my answer, and here is the really neat thing. That answer, that cube root of that trinomial, that was actually hiding up in here in that highlighted yellow part right there. Like, how would you have known that? So without knowing that, you can't just integrate this right-hand side. So there's no easy way out for these differential equations that have x's and y's on the right-hand side. You have to separate them and then integrate separately, the x's and the y's. So let's try a few more. Okay, there are going to be 4 more here, and then this lesson's done. Now, each one of these do bring in some more little issues, right? So be patient with yourself when we see these. This one here, if I write this in Leibniz notation, I would have dy dx is equal to 4xy squared. Okay, it's definitely interesting because it's got x's and y's in there, right? It's got that dependent variable hiding over here on this side. So it's challenging, and we're going to have to get there by separating. So I'm going to put the y's on the left. And to do that, I'm going to divide both sides by y squared. So I'm going to have 1 over y squared dy. That's a weird looking y. And then I'm going to move the dx up to the other side is equal to 4x dx. Now I'm going to integrate both sides. I really only need to put a constant in on one side. I'm going to put it over on the right. I'm integrating y to the negative 2, right? So I have to think about that. What's the antiderivative of y to the negative 2? It's just a power. I don't need to do any substitution. I don't have to do integration by parts. I'm going to get a y to the negative 1 with a little negative 1 bodyguard out there. That's going to equal the antiderivative here, 2x squared plus a constant. Now I'm just going to put constant number 1 for a minute. Time to go and figure out what y is. So right now, let me just rewrite this so it's a little more clear. I have the negative of 1 over y is equal to 2 x squared plus c1. I want to know what y is. I'm going to get there in a couple of steps. First step, I'm going to go and multiply both sides by negative 1 because I'm trying to clean this up and get to just y. And I'll have, of course, negative 2x squared. And then here's the weirdest thing. I'm just going to go plus c. And you're like, no, that can't be right. It's got to be minus c. Well, I haven't found out what this constant is yet. And when I go to find it, I'll get the right value that's there. So I guess technically what I'm saying is, okay, well, there would be a different c here, right? We're going to get this number in a minute. And c2 would be the negative of c1. Mathematicians, when they play this little game, when they're like, oh yeah, it's no big deal, we haven't even found the c yet, they have a little phrase for that, an acronym. This is WLOG, and it stands for without loss of generality. Two L's maybe. So I'm just trying to keep this general, and that'll still keep it general. Well, now I'm going to flip both sides and say, all right, y, if you want to know what it is, it's going to be 1 over negative 2 x squared plus some constant. I'm just about done, except I want to know what that constant is. So here's where I go and grab the information that they gave me. And up at the top of the page, it says if you put 0 in for x, we need to get negative 1/10. So y at 0 would be 1 over negative 2 times 0 squared plus a c, and that needs to be negative 1/10. Well, I'm going to end up having 1 over c is equal to negative 1/10. Okay, c is equal to negative 10. That's the only way you can get that to work. So here's my final answer. The solution to this separable differential equation, this y function, it's made up of x's, right? That's why some people like to celebrate that and say, of x. It's 1 all over negative 2 x squared minus a 10. Now, another way you could write that, if you chose, is you could say, oh, let's just put one negative sign in the top. So arguably this might look a little bit better. There you go, 2 down. Had to do it by separating the x's and the y's. It was the only way to accomplish this task. This next one has a couple of issues in it. So it's going to take a couple of pages in order to solve the whole thing. So don't be stressed by it. Just, we'll kind of work our way through it and be patient with yourself because there are a few curveballs that are getting thrown at you here. So it says y prime is equal to a 4 all on top of a 2. And at first glance, I'm looking at it going, why would they do that? Why not just put a 2 in the top? But they wrote it 4 on top of a 2 multiplied by, that's a problem, y plus 1. So again, there's the answer hiding in the question. And we have to go and figure out, how is this going to work? How can we figure out what y actually is? I'm going to have to do it by separation of variables. It's the only way we can get started here. So their story, written in Leibniz notation, is dy dx is equal to a 4 sitting on top of 2 times y plus 1. I'm going to trust that whole 4-2 thing, that maybe that's important. And I'm going to go and take the 2, y plus 1, with me over to the left-hand side. dy is equal to just a plain old 4 dx. And then I'm going to integrate both sides. Okay, this is where it gets a little bit strange. It turns out there are a couple of options for how to integrate that left-hand side. Integrating the right-hand side is actually pretty easy, right? It's just going to be 4x. But what are we supposed to do with that left-hand side? So I'm going to split my page here and just show you 2 different ways that you could dive into this. Depending on what you notice, and how you want to attack it, you might find yourself doing this option, or you might find yourself doing this option. They both work. They both work, but they each have their own little challenge in the middle. So one option to try to solve this integral here, this antiderivative, is you could do substitution. Okay, from the first lesson of the chapter. You could say, you know what? I think substitution would work well. I'm going to let b be the blob y plus 1. So then db dy is equal to just 1, or another way to say that, db's are equal to dy's. And you then rewrite the question. You say, oh, well, this is now on the left 2 b db. That's actually going to be pretty easy to do. And then over here on the right-hand side, we've got this integral of 4 dx. Okay, well, the integral of 2b, that would just be b squared. And the integral of 4 would be 4x plus a constant. But remember, the b was actually y plus 1. So right now you've got this. Okay, so that's one way out. You could do some substitution, and you could get yourself to that point. Now I want to get the other option to at least this point, and then we'll go and we'll solve for y. We still haven't solved for y yet. But what if you didn't do that? What if you didn't do substitution? What if you just expanded that out? You saw the 2 bumping onto the y plus 1, and what if you just simplified and said, okay, if I simplify it, does it actually get better? Well, you then have the integral of 2y plus 2 dy is equal to the integral of 4 dx. And at first glance, it seems like it's pretty nice. You'd have y squared plus 2y is equal to 4x plus some sort of constant. But our next mission is going to be to go and solve for y. And so this is tricky, because in order to solve for y, I have to do that process that not a lot of people like, called completing the square. This was back from Math 11. And you'd have to go and create a perfect square trinomial by adding 1 to both sides. And so you'd say, oh, okay, well, if I write this as y squared plus 2y, and then if I added 1, then I'd be okay. But then over on this side, technically I should go and add 1 here too. I should go 4x plus 1. But remember, I still have this c, right, that I haven't figured out yet. So I don't even really have, it's so weird, I don't even have to add the 1 to this side. I could just go with a slightly different c. And I could say, okay, well, we're now here, we've got y plus 1 squared, because that was a perfect square trinomial. And on this side, I could just go 4x, And then I'm gonna blend these two things together like this and just say, yeah, it's gonna be 4x plus some sort of other constant. And there's that whole without loss of generality thing, right? Because I haven't figured out who C actually is yet. So whichever one of those you like the best, they each have an advantage and a disadvantage there. The simplifying looks nice off the start, but then you have to do completing the square. The other one, you have to invest a little effort right up front and do the substitution. Either way, you can get to here. And now we're going to solve for y. So to solve for y, I have to take a square root of both sides, right? So we've already dealt with one issue, right? Like, do you want to do the complete the square thing, or do you want to do substitution? Like, that alone is challenging enough. And now we're going to deal with another challenge. When I go to solve for y and I write this as y plus 1, over on the other side, I have to introduce this option here of plus or minus, at least up front, in order to be ready to deal with all the different situations that can happen. And then I've got this 4x plus some constant that I haven't even figured out yet. And so this is a big challenge, is we're going to have to be ready to address this question of which one do we want. And depending on the actual question, sometimes you want the positive version, sometimes you want the negative version. You have to do a little more exploring with the initial condition. You have to do more exploring with this info they gave us back up at the top right here, where they said, oh, if you put 1.5 in, you have to get -4. That was their question, their initial value. So that's what we're going to be working off of, and we're going to go over to the next page to do it. So right here, let's keep going on this. Right now, if I solve for y, I could say y, it's a function of x, it's equal to, okay, moving this 1, I'm going to have a -1, and then I still haven't decided yet. Add or subtract, it's going to be one of those, the square root of 4x plus some constant that I just haven't established yet. Well, we're going to find out whether it's plus or whether it's minus right now, as soon as we look at this initial condition. They said when you put 1.5 in, you have to get -4 out. All right, so on the other page, they had this. Let's see what that requires. So y, when 1.5 goes in for x, that would be a -1, and then I still haven't yet firmly decided whether I should add or whether I should subtract. I've got this square root, and right now I'm going with 1.5 and then plus c, and that needs to work out to -4. They said so. Okay, I have -1. It's going to either be add or subtract the square root of 6 plus c, and then I end up with -4. Oh, the only way I can get -4, if I start off with -1 and I'm trying to get to -4, I'm going to have to subtract 3. Now, it's not always negative, but in order to get this, -4, that's here. Another way to look at it, let's just keep isolating here. If I go and add 1 to both sides, I would have plus or minus this root of 6 plus c needs to be -3. If I take -4 and add 1 to both sides to move that -1. This time, and everyone's different, but this time, it's going to be the negative. Okay, so if I go with the negative, I'll be all right, and I'll have this need, the negatives will match up, and I'll have this need for the root of 6 plus c to be 3. Well, if I'm rooting something and getting 3, the stuff under the root's got to be a 9. So 6 plus c is 9. c has to be 3. Okay, we're there. Here is the solution to this story. Y, which is made up of x's, is actually going to be -1. And this time, it's just subtract. It's the only way you can get this to work. The square root of 4x plus a 3. Now, before we go and look at the last 2 pages, the last 2 examples, let's just backtrack on this just for a second and see what's happening here. So I'm going to go back up page or so. This issue here, yeah, it doesn't matter which one you pick. You'll get there, right? But that was the first little hurdle in this story, was how do we deal with this y plus 1 thing there? That way you can solve for y when you're done. Substitution probably works the best if you don't want to complete the square. So that's done, and now you're going to end up integrating, and then you've got something that in this story it was y plus 1 squared. Next time you do it, this part right here might just be a y. You might say y squared equals 4x plus c, and you're going to have to take a square root. So maybe it's not always the complete the square issue, but if you have at this point a y squared and you're taking a square roots have this plus or minus issue. So you're always going to have that show up where after integrating you have a y squared and then you're solving for y. But the initial condition will tell you whether it needs to be the plus or whether it needs to be the minus. And in this particular story, it needed to be the negative version of the story. That's why it says minus the root of 4x plus 3. Okay, just 2 more of these on-the-job training deals. This one here, it looks super intimidating, but it's actually not going to be too bad. We'll have it easily done in a page. First thing I'm noticing, the answer that I'm looking for, which is called y, is embedded in the differential equation. It's over here, right? It's inside the cosine, and it's down here in this denominator. So that's complicated. I need to do this one by separation of variables. It's the only way to get it to work. So I'm going to put my dy's on the left. I'm going to multiply both sides by 3y squared. So I'll have 3y squared. I'm going to divide by this cosine squared of y cubed. Okay, so I've got cosine squared y cubed. I'll also still have the dy. Now, what's left over here on the right-hand side? Not much. E to the x dx. So I'm doing my usual game, right? I'm separating the variables, and y's are going this way, x's are going that way. The dy stays on the left, and the dx is going to go over to the right-hand side. Okay, well, I now have to do 2 separate integrals. And if I was to just start integrating this one over here on the left, it looks really intimidating. But if I just rewrite it a little bit, suddenly it doesn't look quite so bad. This is actually going to be, now dividing by cosine is secant, right? And it's squared. So this is secant squared of y cubed times 3y squared dy. That's actually going to work out really well, even though it looks complicated. And then we've got our e to the x dx. And yeah, we're going to integrate both sides. So remember we talked about how there are like tools of the trade, and there are 2 methods that we've got for doing integration. The one we did just for fun was parts, but the main one was substitution. That substitution is going to pay off right here. So it'll be a little tool we use right at this moment where we can say, hey, you know what? There's this blob sitting right there. And oh, look, there's the derivative sitting right nearby. So why don't we go make it official, and we can say b for blob will be y cubed. So then db would be 3y squared dy. And how perfect is that? Because I see it sitting right there, 3y squared dy. So I'm going to rewrite their story. I don't like theirs. I'm going to rewrite it with b's. This is the integral of secant squared of b db. That's so nice, right? So all this stuff right here, all that got swapped out for a db. And then over on this side, yeah, I've got this integral of e to the x dx. Well, secant squared, it sounds intimidating, but it ain't so bad. That's just tangent. So this is tangent of b. And then integrating e to the x, well, that's the one function where when you take derivatives or do integrals, nothing happens. It's just e to the x. It would be plus a c, though. Okay, we're almost done, except our story didn't have b's in it. It came with y's, so I'm going to go back. Tangent of y cubed, remember, you're trying to get to y, would be e to the x plus c. All right, as I look at the left side, y was sitting there, it got cubed, and then it got tanned. So as I go to undo that process to get back to y, the first thing I have to do is untan it. I have to inverse tan it. So that's arctan or inverse tan, whatever you want to call it. So I'm going to be untanning both sides, and that's going to show up as me untanning this e to the x plus c. I'll untan the entire sum, e to the x plus c. That's y cubed. I would now have to cube root that in order to come up with my final answer. This one didn't actually give me any initial value, so I have no hope of finding what that c is, but I can just give people a general solution and say, well, generally it looks like this. It's a cube root, oops, not Tom, tan of inverse tan, I should say, messing a couple things up there, inverse tan of e to the x plus c. And that c is inside that bracket, inside the inverse tan, underneath that cube root. It's not hanging out here, not this time. And if you had an initial value, then you could actually go and find out what that c is. So pretty intense looking solution, but it does work. It satisfies that separable differential equation. Okay, one more. Remember how I was saying each one's got a little curveball to it, a little hurdle to it. This one here looks like it doesn't want to separate. When you see that e to the 5x squared minus y, at first glance, I'm kind of thinking, wow, there's no way that I could pull that apart. Over here, the dy dx, okay, no big deal. And I see the x, okay, that's fine. But what do you do here with this e to the 5x squared minus y? Well, how about this? I'm just going to move this a little bit. Thinking back to just Math 10 for a minute, just thinking about patterns. If I had, I don't know, a to the b, and I was dividing by a to the c, in Math 10 we would say, oh, well, that's just a to the b minus c. Let's just do that in reverse. The a is like the e, and then the b minus c is this 5x squared minus the y. So I could actually rewrite their story in anticipation of getting ready to do some separation. I could say, okay, dy dx is equal to, I'm going to write this as a fraction here. The x is just sitting upstairs. There's an e to the 5x squared, and then it's divided by an e to the y. If you did that division, you would subtract 5x squared minus y and just put that as an exponent on the e. So I think that's fine. And now I have the ability to separate it. I can bring this e to the y up to the left, and I'll have e to the y dy is equal to, and over here I'm going to reorder this here, e to the 5x squared times an x times a dx. And then we're going to integrate both sides. Now the e to the y is actually going to be pretty quick and easy. The other part, now we're going to do a little substitution. We're going to say, hey, check out that blob. The derivative is pretty much sitting right here. Yeah, it's off by a factor of 10, but that's no big deal. So remember, we talked about tools of the trade, right? Substitution. So we're using that now. We're going to use it here. And we'll say, oh, here's a good substitution. How about a blob? That's 5x squared. For that blob, db dx would be 10x. Okay, well, I don't really want the 10, and I want to move the dx up to the other side. So if that's true, then two moves at once here. 1/10 db would actually equal an x dx. So I multiplied both sides by dx and divided both sides by 10, and that now beautifully matches up with that, right? There it is right there. So the x dx is coming out, and a 1/10 dB is going in its place. So here's a new integral that I like better. How about the integral of e to the b with a 1/10 just floating around and a dB? Okay, now accomplishing the integrals. Let's do this. So doing this one, that one, nothing really happens. That's just going to be e to the y. Now over here, doing this, I'm going to basically have an e to the b with a little 1/10 floating around, plus a constant. The calculus is pretty much done. It's just some algebra here now. I'm going to have e to the y is equal to 1/10 e to the 5x squared, because I really need to get away from the b's now, and then plus a c. Okay, you need to get to that y. You need access to it. And the only way I can get to that y, in order to solve for y, I'm going to have to take the ln of both sides. So if I take the ln of this side, take the ln of that e to the y, and I'm going to do the same thing over here. Okay, well, when I do that, when I look over on that left-hand side, the y comes down, and then there would be this ln of e. But the ln of e is just 1, and it equals the same old stuff over here. So I don't have to worry about the ln of e. Hey, I'm done. Y, which I'm just going to celebrate the fact that I now know it's made up of x's. It's actually going to be the ln of 1/10 e to the 5x squared plus a c inside that logarithm. And they never gave me any numbers to actually go and use to find out that c. So I'm just going to say, yep, there's the general solution. Maybe not a specific one, maybe not a particular one, they might say, but there's a nice general solution to that separable differential equation. So looking at this one big picture, yes, it was troubling off the start because it had x's and y's in the story, right? So the fact that you actually see this y here means, oh, it's going to be tough. And it was a little bit challenging separating it. We needed to use some exponent laws to do it. But once you separate the x's and the y's, then you're in business. And yes, along the way, you might have to do integration by substitution in order to pull that off. And that finishes up our fourth lesson. In the next lesson, we're not going to say, oh, let's look at another technique for doing this. In the next lesson, we're going to say, well, what if we're stumped? What if we've exhausted our methods for trying to do these differential equations? What if you can't just integrate? What if you can't separate and integrate twice? We're just going to have a backup plan, and those are called slope fields. So they'll be for anything that we can't quite work with.